Hello guys, nice to see you.
Good afternoon, Professor.
Hi, how was your weekend?
Good, actually. Yours?
Yeah, not bad. So today we, as I mentioned last uh, class on Friday, today we start new topic of our course, which is thermodynamics and molecular physics. So it's another quite important field of physics, which not studied in many details during this course, since we have only a few weeks left for this whole topic, including some thermodynamics and molecular physics. However, we are going to go through the main topics and discuss the main concepts which build up the foundation of thermodynamics and molecular physics. Yeah, hello, hi. So thermodynamics is actually a field of study which deals with changes in temperature and state of matter, like solid state, liquid, gaseous state, because of exchange of some energy between different bodies, different systems, and its surroundings. There are three most common ways of exchange energy between systems. So one of the most common for us is thermal conduction. So when we have one side of the body kept at higher temperature, another side of the body kept at lower temperature, and there is some, because of this temperature gradient along the body, there is some heat transport. Also convection, when hot and cold parts of the medium are exchanging, so they circulate in the medium. And also radiation, so that is involves electromagnetic waves. So every body which possesses some temperature irradiates some energy in form of electromagnetic waves, and its spectral distribution depends on temperature. So that will be discussed more in details in future, but definitely this is the way how exchange of energy can happen when there is no some intermedium between two bodies. For instance, we have the sun, which produces a lot of energy because of thermonuclear fusion processes in its core. And we still receive on Earth a lot of this energy in the form of electromagnetic waves, which reach us, and they are in quite broad spectrum, from infrared to ultraviolet. And this is possible only because radiation involves this heat transfer via electromagnetic waves, because we don't have any medium in between the sun and the earth. It's just vacuum. So this is only one possible way how energy can be transferred. So thermodynamics closely relates. So it really, the way how bodies respond to getting or losing some energy closely related to their atomic, like molecular structure, because it defines thermodynamic properties of the material of the system. However, it operates with macroscopic parameters, temperature, for instance, pressure. So these parameters depend on microscopic nature, but as a result of these microscopic processes which happen in the system, they actually can be characterized by macroscopic parameters. So kind of some average parameter for whole system, which are temperature and pressure. So temperature is one of the key parameter for in the field of thermodynamic study, and it can be explained some approximation as a measure of internal energy of the system. And this internal energy depends on, it is defined by the kinetic energy of its particles, which forms the system, like atoms or molecules. So it could be a kinetic energy of translational motion, rotational motion, vibrational motion, and also potential energy of interaction between components of the system, these particles, how much they interact between each other. And that also will define thermodynamic properties of the system. And the internal energy accumulated in this system. So the temperature is is the main parameter which describes, quantifies this internal energy. And we can definitely, by touch, distinguish if object is cold or warm. But in terms of being more quantitative, we need to propose some ways to measure temperature and do it reproducibly for everyone, everywhere. And for doing that, you need to find some parameter which changes with temperature and calibrate this change of this parameter to certain two reference points. So what can be done? For instance, let's say we have some metal rod, like metal stick. With increase of temperature, it will expand. So its length will increase. It's an option to measure temperature. So if you measure these changes with certain step in change of temperature, let's say you have 2 points, reference point, you measure length of this metal rod, then you can calibrate, divide this change by certain number, and you will have a thermometer. But it's very tiny change. So this expansion, thermal expansion, is very little, and it will be a big challenge to measure accurately the change of the length of this rod in order to have a precise thermometer based on this. So for this, in order to overcome this challenge, most common thermometers are based on liquids. They are based also on thermal expansion, but not like linear thermal expansion, but like three-dimensional volumetric thermal expansion. And the combination of volumetric thermal expansion with the design of the thermometer itself provides us an ability to measure temperature accurately by using these thermometers. So why it is done like this? So we have some big volume, like relatively big volume of liquid, which is comprised in the thermometer, some glass. And then to this relatively big volume of liquid is attached very thin glass pipe with a very small radius of the cross section. So as I mentioned before, change in the volume or length of objects because of change of temperature in relatively narrow temperature range, which we usually deal with, is quite small. So, however, since the area, cross-section area of this small pipe, which is attached to the tube, which is attached to the big volume of liquid, even very tiny change in volume will result in quite large increase of the level of this liquid in this tiny tube. And that's why we can accurately measure it. So this is kind of engineering approach to utilize a feature of volumetric expansion because of change of temperature of liquid and making this possible for accurate measurement. So once we have such a device, which you obviously had in your hands for sure, and we quite usually use them to measure temperature of the surroundings outside, to measure temperature in like our body temperature. So there are mostly two types of liquid thermometers. One with mercury as the working liquid, and another with some ethanol, like colored ethanol. So there are benefits and disadvantages. First of all, benefit of mercury is its very high thermal conductivity. So it means that when we put this main volume of the thermometer in some medium, it will very rapidly conduct heat to the upper part of the mercury pillar, and all volume of mercury will reach the same temperature, which is kind of very important to have accurate measurement. Also, it doesn't wet the glass. So that's why we don't have this menisc at the surface of glass, which helps to accurately distinguish by visual observation where this level of mercury is located. Ethanol-based thermometers, they have advantages because ethanol doesn't freeze so easily as mercury. So mercury is like -40, it cannot go below, it will become already solid and will damage the thermometer. So ethanol can go to like -70. However, it's not so accurate. It wets the surface of glass and it doesn't possess such high thermal conductivity. So in order to calibrate the thermometers, we usually do the following. So we need some reference points. And since water is one of the most commonly distributed substance in the world, we operate quite often with water. So one reference point is so-called icy water, when we have a mixture of ice and liquid water, which is considered in the Celsius temperature scale as 0. Then we go to another reference point, which is boiling water. So boiling water, we need to make a remark here. Boiling temperature depends on pressure. So this is defined as boiling temperature at normal conditions when we are at sea level. So then boiling temperature of water is considered as 100 Celsius. It's kind of arbitrary definition. We could choose some other numbers, and that is actually done in other scales of measuring temperature. For instance, Fahrenheit scale assumes that freezing point of water, like this icy water temperature, is 32 degrees of Fahrenheit. But we are more accustomed to Celsius system. Then we have these two reference points, and change in the position of this liquid in the thermometer, we divide by 100. Then we can, within this accuracy of 1 degree Celsius, if, for instance, from 0, we know where this level is located at 0 at Celsius, and then if we put in some environment, it increases by 50% of this calibrated range from 0 to 100. We know that this corresponds to 50 degrees Celsius. So this is how this basic approach to measure temperature, like and calibrate thermometers, is working. However, there is a disadvantage of liquid thermometers because not all liquids expand linearly with increase of temperature. That is a problem because even if we calibrate two extreme points, like reference points for 0 and 100, it will be some uncertainty in between because one thermometer is one liquid can expand not linearly and differently from another thermometer, which will expand non-linearly but in a different way. As a result, we cannot have a reliable instrument to measure temperature because like every detector should possess some linear dependence on the detecting parameter. That is the key requirement for a reliable detector. That's why, let's maybe now I change the screen and draw something. Oh, there is a question if they use distilled water. Yeah, I mean, you need to use pure water for these experiments, because if it's some salty water, and of course we know that freezing temperature will change of salty water, so we need chemically pure substance. Then we can define what substance it is. If it's not chemically pure, then it's some mixture which will possess different properties. Yeah, but good question. So one way to go for truly linear detector is to switch to this constant volume gas thermometer. And the concept is the following. So we have some We have some volume with gas, some tube attached to it. So this is level, like volume of which is filled with gas. And this volume is kept constant. So on top, we have some level of, let's say, mercury. So here is the interface between gas and mercury. So we have what? We have some mgh. So better if we deal with pressure, then we go for rho, for density of this material, rho gh. It's pressure of this pillar of mercury, plus we have some pressure of atmosphere. So that will define pressure in this volume. But if we start to heat it up, so we start to increase temperature, this volume will tend to increase, like because this gas would like to increase in volume. And what is done in such constant volume thermometer, you need to add certain amount of this mercury to compensate this change of the volume. So you are sure that at any temperature, your gas stays at the same temperature. Stays at the same volume, and temperature is changing. So if we have this condition that every time we change temperature, we correct this expansion of gas by adding more pressure from outside and keep volume constant, then we can plot such dependence. We will have temperature and pressure. So pressure we can always define as atmospheric pressure plus this pressure of the pillar of the mercury on top. It will change, depends on temperature. And if we calibrate this for two reference points, it will be 0. So this will be in degrees Celsius, 0 and 100. We can make a straight line between these 2 points, and doesn't matter. So it is shown experimentally. We always will be at this linear dependence. So at any temperature, pressure at constant volume will follow this linear dependence. This is very important because we get a truly linear detector of temperature. However, it brings us to some very fundamental finding. So if, for instance, we have such a plot, here will not be in proportions, but the key concept you will figure out. And let's say we have 3 different gases. We have thermometers with 3 different gases, and they are calibrated for these reference points. So they will have these kind of linear dependencies. They will be different, but all of them will be linear. But slopes will be different because it's defined by the properties of the gas. Say, or some initial starting point. So you can start these measurements at different pressure. So what we can see if we extrapolate this linear dependence for all 3 cases, it will come to the same point when pressure will be vanished. there will be zero pressure inside the system. And this is minus 273.50 degrees Celsius. So this is some special temperature. Why it's so important? Because this is the minimum temperature which can be achieved. Why? Because physically it's impossible to get negative pressure. So if you go to lower temperatures, imagine that we can go to lower temperatures and extrapolate this linear dependence further, we would end up with some negative pressure, which is impossible. So if you have some amount of atoms which forms this gas confined in a fixed volume, its pressure can be always only bigger than zero, so it cannot be negative. That's why this temperature minus 273.15 Celsius is so-called like minimum temperature or absolute zero. So absolute zero comes from another scale of temperature, which is absolute, so-called absolute scale of temperature. Since we have such special temperature, minimum temperature, it makes sense to set it as zero, like absolute zero, and then use another reference point at higher temperature to end up with absolute temperature scale. And such reference point was decided to be the so-called triple water triple point. So this point is it's a temperature at which it's a unique combination of temperature and pressure at which three phases of water can coexist simultaneously in solid, liquid, and vapor, like ice, water, and vapor. And this temperature is 273.16 degrees Celsius. So, sorry, not degrees Celsius. So in absolute scale. So when we have absolute temperature, it's temperature in Celsius plus this 273.16. And then we have the same range, so 1 Kelvin. So this is already absolute temperature measured in Kelvin, is equal to 1 degree Celsius. But keep in mind that we don't call degrees Kelvin. It's wrong. So we have degrees Celsius, degrees Fahrenheit, but in the absolute temperature, we operate just with Kelvin. And then 0 degrees Celsius will be equivalent to this 273.16 Kelvin. Okay, once we define some scales for measuring temperature, in particular, also we define the absolute temperature scale, and that is important because we will use it for all further calculations in physics. We always operate with absolute temperature scale, and temperatures are measured and used in equations in Kelvin. We can proceed further and let's discuss how properties like size of the different bodies changes with change of temperature. So let us consider thermal expansion of solids and liquids. So there is linear and volumetric thermal expansion. So change in the length of an object can be calculated as some linear thermal expansion coefficient alpha times initial length times change in the absolute temperature. So if we want to calculate change in the volume of some solid or liquid system, that would be equal to some volumetric thermal expansion coefficient, let's call it beta, times initial volume of the system and times change in the temperature. So now let us try to figure out the relationship between these two coefficients, alpha and beta. So for this, let us consider some box. With size, let's say L, W, and H. And consider that it possesses some uniform properties in all directions. So when it expands uniformly in all directions. And in this case, we can consider that each of these sides expands according to some linear coefficient, like linear thermal expansion coefficient alpha. So we have some initial temperature, have some initial volume, which is equal to the product of these sides, L times omega times H. And we have increase in temperature, initial temperature plus delta T. And then, of course, as a result, we have some increase in initial volume, V initial plus delta V. So let us figure out what will be this volume after thermal expansion. V plus delta V will be equal to, so as I mentioned before, we consider changes in each side of this box, and it will be plus delta L plus delta omega plus delta H. So it will be L plus delta L, then times omega plus delta omega, and times H plus delta H. So now we know equations which describe this change in the length of the sides. So it's actually this equation. So we can use this alpha coefficient to describe them. So we will get alpha plus L plus alpha times L times delta T. And we do this for each of these sides. So it will be omega plus alpha omega delta T and H plus alpha H delta T. So now we can factor out L, omega, and H. We will end up with such equation. It will be L omega H times 1 plus alpha delta T Q. So this is initial volume. We can rewrite this. Initial volume times this 1 plus alpha delta T Q. And taking into account that, maybe let's write it here. A plus B in third power can be written as A cubed plus 3A second power times B plus 3A times B squared plus B cubed. So if we take this into account and open this parenthesis here, we will end up with another equation where it will be initial volume times 1 plus 3 alpha delta T plus 3 alpha delta T second power and plus alpha delta T third power. So here we need to take into account that the product alpha times delta T is smaller than unity for like our common range of temperature from like for delta T like up to like smaller equal to 100 Kelvin. Why? Because alpha is very small. So as I mentioned before, this thermal expansion, it happens, but it quite small change in length or in volume. So alpha coefficient of linear thermal expansion is a small value. And if we multiply it by not very big change in temperature, like within 100 Kelvin, this product will be less than unity. Taking this into account, we can neglect with these higher orders of this product because it will be much smaller than unity times 3 alpha delta T. And that's why we can rewrite, I mean, here is better to write that it's approximately equal. It's some approximation, but quite reasonable approximation. It's V initial times 1 plus 3 alpha delta T. So now what we can do, we can divide left side and right side. So left side is this and right side is this. We can divide by initial volume. As a result, we will get 1 plus delta V divided by V initial is equal to 1 plus 3 alpha delta T. And so 1 and 1 we cancel out. And from here, we can write that delta V is equal to 3 alpha times V initial times delta T. And with analogy to this equation which we wrote at the beginning, we can write that beta is equal to 3 alpha. So we get such a dependence between the linear expansion coefficient, thermal expansion coefficient, and volumetric thermal expansion coefficient. And in following the same concept, we can also show that the change of the area of some surface due to thermal expansion will be also equal to, let's say here, delta A, change in area, will be equal to 2 alpha times initial area times delta T. So actually thermal coefficient of linear thermal expansion will provide us information of surface and volumetric thermal expansion coefficients. We just need to multiply it by 2 or by 3. Okay, so we were talking here about expansion of some solids or liquids and like thermal expansion. And thermal expansion automatically means that the density of the material reduces, because if we don't change the mass, we increase the volume, that results in the decrease in density. However, not all materials, specifically it's a unique example is water, it behaves kind of unexpectedly. So if we plot density of water as a function of temperature, let's say it will be here degrees of Celsius. So we will see something like this. It will first increase somewhere up to 4 degrees Celsius, and then it will decrease. So this is very unusual. So it means that within this narrow temperature range, like from 0 to 4 degrees Celsius, it happens that water doesn't expand, it actually shrinks, reduces in volume because of increase of temperature. That's unusual behavior, and this is one of unique features of water. And just keep in mind that it's actually this feature of water probably played one of the major role in evolving of complex life on our planet, because this is the reason why water is freezing on the top, not that it doesn't freeze from the bottom. So what happens, let's say if we have some cold water, which with temperature something like 6-7 degrees Celsius, and external like air is colder, so it cools down the water. And with this range from, let's say, 5 to 7 degrees Celsius, decrease in temperature results in the increase of density. So means that cold water will go down, and because of convection, and warmer water will come up. However, when it reaches 4 degrees Celsius and continues to cool down, it has this inverse dependence. So now with further cooling, density becomes smaller. When we cool down from 4 degrees closer to 0 degrees to freezing point, density becomes smaller and means that this cold water doesn't go down because of convection. So it stays on the surface until it forms the ice. And that's why if it gets colder and colder, ice builds up on the surface and the lower layers of water, they remain liquid at temperatures close to 4 degrees Celsius and don't freeze. So that means that all these marine habitats are not killed because of frozen water in all volume. And since initial evolution of life on our planet was going on in water, this feature of water to freeze only on top played a very important role for existence of complex life and ourselves including. So now let us go to the, so maybe we are running out of time, so maybe I will just announce what kind of topics we are going to discuss during our next class. So today we had some introduction into thermodynamics, explained that it describes change of temperature and state, liquid, gaseous, and solid of different materials. Introduce some macroscopic parameters like temperature, pressure, volume of the gas, and we will discuss in more details during our next class on Wednesday some relationship between macroscopic parameters of ideal gas. Ideal gas is the system where we have particles like atoms or molecules which do not interact with each other, only in that cases when they collide with each other. So, but other from that, there is no interaction. We neglect with any forces which interact with of interaction between these particles of the gas, and this system is called ideal gas. So we will discuss which relationships exist between these macroscopic parameters of gas, temperature, pressure, and volume. And further, we will go to the discussion of heat and internal energy. So what is definition of internal energy, which we already kind of discussed a little bit, and also what is heat and how we can change internal energy by transferring energy in different ways from one system to another, and which laws these transfers follow. So this is our topics for discussion for next time. Thank you very much for your attention, and have a good evening.
Excuse me, Professor.
Yes.
Can I ask a question?
Sure.
So the question is related to the course itself. Would we have test questions on long upper or midterm questions or final questions related to thermodynamics?
Yes, we will have homeworks and thermodynamics, molecular physics. We still have like few, I'm not sure exactly, but few weeks until the end of the course. So we will, for this midterm, we will not have, I believe, because next midterm, like final midterm will come to, so when do we have it? On 17th?
This week
Yeah.
Saturday. Yes.
Okay. So we have this week, so it will not be included in the last midterm, but final exam should include some topics from thermodynamics and molecular physics.
Okay, thank you.
You're welcome. Okay, guys. Bye. Take care. See you next time.
Goodbye. Have a nice day.
You too.